So as you know that in the last lecture we started to talk about a phenomena that we call inductance, and we said that inductance is basically the counterpart of capacitance. And in capacitance we know that the electrical energy is stored in between the dielectric medium. But when we talked about inductance, as the topic is not yet concluded, we did not see that how an energy is stored inside an inductor. All we did in the last lecture was we tried to take an example of solenoid, and then we calculated the value of magnetic flux density that is produced when a current is passed through that solenoid. We derived the expression for that, and the expression was basically B is equals to Z hat mu Ni over L. I is the amount of current that is flowing through the solenoid, N is the total number of turns, L is the length of that solenoid. And after that, we introduced two concepts that we talked about. We said that we have self-inductance and we have mutual inductance. And while defining those two things, we uh, used a term which was called magnetic flux linkage. We said that whenever the flux that is produced by a coil itself, it links with itself, then we say that this is self-inductance. And whenever the magnetic flux that is produced by one coil links with another coil, we'll say that it is mutual inductance. So we just introduced these two concepts. We still haven't figured out the value of, or we still haven't derived the value of magnetic of inductance, of self-inductance or mutual inductance. So in this lecture we'll try to divulge ourselves into the phenomena which we introduced into in the last lecture, and which was called self-inductance. So in order to understand self-inductance, it means that while we defining while we defined the self-inductance, we talked about magnetic flux linkage. It means that we have to drive an expression for magnetic flux linkage. We have to figure out how do we quantify magnetic flux that is linking with itself. And when we do that, we'll be able to understand how the inductance basically opposes the sudden change in current. We have always studied that a solenoid or an inductor of any shape, it has the characteristic of suddenly of resisting a sudden change in current. What happens is that before going into the detail about self-inductance, I'll try to talk a little bit about that concept. Uh, what happens is that we all know that according to Faraday's law of inductance, we will say induction will say that whenever there is a flux which links with a conductor which is placed in its vicinity, whenever that flux changes, as a result an EMF is induced in that conductor. So when we are talking about a coil itself, and we are saying that its flux is linked with itself, then whenever the amount of current that is flowing uh, through that solenoid or through that inductor, it is constant, then as a result the amount of flux that is being generated is also constant. And even if that flux is linked with the coil itself, there will be no resistance against it. But the amount of current changes whenever the amount of current changes, we'll know that if the I changes, the value of B will change. And if the value of B will change, then it means that the amount of flux is changing. As a result, if the magnetic lines of force are linked with that coil itself, and the magnetic flux is changing, it means that that change in electric flux that change in magnetic flux sorry that change in magnetic flux will generate an EMF, and that EMF is going to oppose the current, the amount of current that will flow due to the EMF that is generated as a result of this change in flux, that will oppose the current that was already flowing in that solenoid. So as a result, that opposition is basically the reactance of uh, inductor. So you know that whenever we talk about inductance, we talk about AC. In case of DC, we have already studied that in case of DC, the inductor behaves like a short-circuited path. But whenever we have an AC flowing through an inductor, as a result, we will have a reactance, and that reactance basically is going to be the thing which opposes sudden change of current. Okay, so that's just a concept that I wanted to deliver to you. So that is self inductance. Now, what we'll do here in this lecture is that we'll try to figure out that flux linkage. We usually uh, represent the flux linkage by capital lambda. So we have to calculate an expression for this capital lambda. And in order to do that, we know that this is basically flux linkage, and in order to calculate the value of flux linkage, we need to calculate the value of flux itself first. So what is the value of flux? We have already studied that flux for any surface which has surface area S is, sorry, B dot ds. We calculated this value two videos back, I guess. So the flux is B dot ds. B is the number of lines passing through area, so the per unit area multiply the area itself. So he's saying that in a solenoid with an approximately uniform magnetic field, the flux linkage of a single loop is going to be, what will be the value of flux in this case? We have already figured out the value of B. We'll put in the value z hat mu n I over small l, and this is dot zs. So why are we taking the unit vector of surface area vector to be z? Because we are considering it to be a circular, a number of circular loops. So in order to calculate the area of that circular loop, we will look from the direction of z. So z hat into ds, and we will integrate this uh, for the surface area. So if we say that the total surface area after integration is capital S, then we will write this equation as mu n I s over L. So this is basically the value of flux that is inside the cross-sectional area of that loop. So if we want to calculate the magnetic flux linkage of A, this is for a single circular loop, and if we want to calculate the value of flux linkage to all the other loops too, then the flux linkage is going to be n into phi. So this expression will become mu n square I s divided by small l. So this is the structure. This is for a structure which contains multiple loops, as we have seen in the solenoid, and its unit is going to be Weber, of course, because number of turns does not have any unit. So he's saying that this is for a thing or a structure which is like a solenoid, and if a structure consists of two separate conductors like parallel wires or a coaxial cable or something like that, then the flux linkage associated with the length of the wire refers to flux through the closed surface between the two conductors as highlighted by the shaded areas. So he's saying that another if we have another example in which we have two conductors like this is one conductor obviously, and this is another conductor which is placed beside this, and obviously this is a single thing because we're considering self-inductance. So he's saying that the current which is flowing here will be obviously going back from here. So he's saying in case of this type of scenario, the distance between these two conductors is d, then the surface area that will take into account is the area in between these two conductors. This will be the surface area, this surface area that we were taking into account, or the area in which we were taking the value of number of lines. So why is it so? Why aren't we taking the flux inside the conductors? He's saying that we are taking the assumption that the maximum amount of flux that is being linked by this coil itself is in between this the area which is in between these two conductors. The reason is that there is a thing that we call a skin effect in the AC conductors. Whenever the current which is AC and it passes through a conductor, the maximum amount of current will tend to flow on its skin, and the amount of current that flows from the core of that conductor is going to be very minimum. So why it happens is that I think you'll study that in power transmission course. As a result, what happens is that the total effective resistance of a conductor basically increases whenever an AC current passes through a conductor. Just because the maximum amount of current will always pass through the skin, and that is why we use bundled conductors instead of a single conductor for high power transmission lines. Whenever you see a high power transmission line, you'll see three conductors which are separated by a triangle type separator. So you'll think that why aren't we using a single conductor instead of these three conductors that are going uh, uh, from one tower to another, and they are separated by a triangle type separator. The reason is because if we take a single conductor, a single conductor with a larger diameter, as a result that is going to be expensive for us, and but apart from that, the maximum amount of current will flow on the skin of that conductor, so that basically the effective resistance of that a single conductor is going to be way higher than if we take three different conductors and we separate them, because in that case the skin increases. So this is the basically the reason behind that. So he's saying that as the maximum amount of current is flowing at the surface of the conductors due to skin effect, that is why we are ignoring the flux which is inside the conductor, and we are taking this integral in between this space or the surface area which is present in between these two conductors. Whatever the lines of magnetic flux are, they will cross this surface, because if you point your thumb in the direction of this current, you'll see that the direction of magnetic flux lines that will produce are going to be like this. So in any case, these lines will have to cross this area. Similarly, for this case, the lines are going to be like this, and they will also uh, cross this area at every cost. So he's saying that we have taken this area in case of this type of uh, structure. We will take the area which is in between these two conductors. Okay, so there is this. He's saying that self-inductance of any conducting structure is defined as the ratio of magnetic flux linkage. So now we have the value of magnetic flux linkage, and now he's defining the self-inductance itself. Is saying that the self-inductance is basically the ratio of magnetic flux linkage to the amount of current that is flowing through that conductor itself. So for solenoid, uh, this self-inductance will be equals to small mu n square s divided by L. This is for solenoid. And in case of any other, this is going to be flux linkage divided by I. This means this is phi divided by I, and then we have 1 over I, and we have P dot ds. So as you know that for solenoid the expression was this for phi, and the flux linkage expression was this. What we did was we divided this expression with I, so this I cancelled out and all that remains is mentioned here. But in case of any other type of uh, structure like this one, for a generalized expression, he wrote the expression for self-inductance to be L is equals to magnetic flux linkage over I and phi over I, and that is 1 over I, and the expression for phi itself. As this type of structure does not have a number of turns, so you'll see that you don't have the that I here, that N here. That is why we don't have an N here, because we don't have number of loops in these type of structures. So that is why the number of loops is considered to be 1. All that remains is phi over I, and we have generalized this expression. So we have an example pertaining to this self-inductance topic, and in that example he's saying that he's asking us to calculate the value of self-inductance of a coaxial transmission line, and inner conductor has a current I, outer conductor obviously will have a current I, and B is generated. Okay, so he's asking us to calculate the value of self-inductance. So what we'll do is we'll try to draw the scenario that he has given us. So if this is a coaxial cable, then we'll have a sheet which is outer conductor, and then we'll have some space, and then we'll have a inner conductor, and then we'll have another space, and we'll have the sheet once again. So if the direction of current that is flowing through this is this, sorry, this is I, then the current is going through this sheet and it is coming back from this sheet. So the current here is going to be in this direction. This is obviously Z's direction. Now we need to figure out what kind of area we're going to take. Just like the two conductor scenario, like we studied in the last topic, we said that we'll take the area which is in between these conductors. And if we take a look at this scenario, we'll see that first of all we need to know how the magnetic lines of force are going to be uh, found here. So we'll place our uh, thumb in the direction of current, and we'll see what will be the direction of magnetic field. So if our thumb is in the direction of current this, then we'll have, let's try to mention or represent the magnetic field's direction. So this is going to be the direction out of the screen from here and into the screen here. So it means that the area that we need to take into account is basically in between these two conductors, obviously for the whole coaxial cable. So this is the surface area that we'll talk about here. The area between these two conductors, or if you take it here, then area between these two conductors. This means that we need to integrate it according to the whole cylinder, the whole coaxial cable. So this is the surface area, and we'll say that this is a surface area S. This is the radius of internal wire A, and this is B. So this is for some arbitrary type thing, and we'll say this is R. We need to integrate it for the whole R. We know that the value of B that is generated due to the presence of current in this conductor is going to be in the direction of phi, and the value is mu I over 2 pi r. So we have the value of B here. So let's choose a transmission line segment of length L as shown in the figure. We have figured out what kind of a surface we'll need to take into account, and the BE will be everywhere here in the direction of phi, and it will always be perpendicular to the surface that we have considered. So we'll say that in order to calculate the value of phi, the flux, we needed to calculate B dot ds, and for this case, as the value of B will always be perpendicular to ds, so we can say that this, we can ignore this B, and we can say that this will be B ds integral, and this ds, in this ds the thing that is changing is r. So we need to calculate this area for this whole r. Everything else is constant. So what we'll say is that we can write this ds as l and dr. So these are the two sides. L is constant and dr is basically changing, and we have to integrate this whole length from this point to this point. Okay, so we changed it to ldr, and then this is b. What we'll do here is that we'll put in the value of b. The value of b is mu I over 2 pi r, and then we have L, and then we have dr. We'll take the constants out. The L is constant, we took it out, so we have mu, that is constant, we have I, that is constant, we have 2 pi, that is constant. The only thing that remains is dr, obviously, and we have to integrate dr from a to b, so that we take into account all the values of r which is in between a and b. So there is one single thing also, we have this r2, so dr over r. So we'll integrate this and we'll get the value mu I l over 2 pi and log natural b over a. So this is the value of phi. He wanted us to calculate the value of self-inductance. We have found the value of phi. The value of self-inductance was magnetic flux linkage divided by I, and in this case the magnetic flux linkage is equals to magnetic flux. So this will put in the value here, the I will cancel each other, and we'll have mu L over 2 pi and log natural B over A. And the next thing is he told us to calculate the value of self-inductance, sorry, self-inductance per unit length. So that is going to be L as capital L over small l. So we'll have mu over 2 pi and log natural B over A. So this will be the value of self-inductance for a coaxial cable. So these things are pretty simple. All you need to understand in these type of questions is that what is the scenario that is given to you. So the first thing that you'll need to know about is the scenario. Okay, what is the scenario? Like this scenario is the coaxial cables scenario. Okay, so it is a possibility that they'll give you a scenario in which you have a two conductor configuration, then you'll have to solve your example according to that scenario. And if you have been given with another type of scenario, then you'll have to improvise, and you'll have to solve this example according to that scenario. The next thing you need to figure out is what is the value, or what is the surface area that you need to take into account. Like here we identified the surface area to be this thing. We knew that this is the surface area, and we need to take this surface area into account. Okay, so this was the surface area, obviously, and the direction of surface area was also in the direction of phi. That is why this was phi hat, obviously. So this was the surface area once again, and that is why b dot ds was 1. And once you have these two things, we need to know that what is the value of b for that particular uh, scenario. Okay, so now we have b, we have s, then it is very easy for us to calculate the value of b dot ds. We'll integrate this accordingly, and we'll have the value of phi. Once we have the value of phi, we'll have the value of magnetic flux linkage, capital lambda. And once we have the value of capital lambda, we'll divide that with the amount of current that is flowing through that conductor, and as a result we will find out the value of self inductance. So these things are pretty simple. Just bifurcate these type of numericals into its parts, identify the scenarios, identify the surface area that you need to take into account, identify the value of B, the expression of B for that particular case, and then calculate the value of phi, and then you can easily calculate the value of self-inductance for this case. The next thing that we need to discuss is mutual inductance. That is going to be pretty simple as compared to self-inductance, because in mutual inductance the same concept, you'll apply the same concept, but in mutual induction, let's talk about mutual induction. In mutual induction, like we talked about earlier, the magnetic flux is being generated due to one coil, and that flux is basically linking with another coil. Okay, so it means that we have two coils. Like if this is one coil and this is another coil, this is placed right beside the first coil, and there is a current that is passing through this coil. As a result, obviously we'll have magnetic flux that will be generated like this. And as you can see from this figure, this flux that is being generated due to the presence of this current in this coil, this flux is linking with another coil. This is coil 2, this is coil 1. This is linking with another coil, and it has a surface area S2, it has a surface area S1, and it has a number of turns N1, it has a number of turns N2, and the magnetic field density that is being produced due to the current that is passing through the first coil is B1. So he's saying that what we need to do is that we need to calculate the value of inductance due to this flux linkage, which is being produced due to coil 1, and it is being linked with another coil. So for that, it means that we need to calculate the value of phi 12. Phi 12, why are we writing it as phi 12? Phi is being produced due to the first coil, and it is being linked with the second coil. So phi 12 is equals to obviously B dot ds, but here B is being generated due to the first coil, so B is B1, but the area that it is being linked with is the area of the second coil. So this surface area that we're talking about, it is the surface area of the second coil. Obviously, if the second loop, which is the second loop, it consists of N2 number of turns, it is not a single turn, but it is the number of turns, then all the turns are coupled by B1. So as a result, if we want to calculate the value of flux linkage, we'll have to take into account all the number of turns that are present in this coil, because all turns will link with the uh, flux that is being produced due to the first coil. So we'll take into account the number of turns, and we'll take into account the flux that we calculate from this expression. So as a result, the flux linkage is going to be N2 integral of B1 dot ds, and this integral is going to be according to the second surface. And if we want to calculate, now we have the value of flux linkage. If we want to calculate the value of inductance, we will say that flux linkage of 1 with 2 divided by the current which is passing through the first coil, that is going to be N2 over I1 and S2 B1 dot ds. So this is basically the value of mutual inductance. This is the value of inductance of second coil due to the linkage of flux that was produced by the current flowing in the first coil. So this is the expression for that inductance. So this type of mutual inductance is uh, basically the application of mutual inductance. The most wide uh, application of mutual inductance you'll find is in the transformers, because the transformers basically work on the principle of mutual inductance. I know you have studied this on the fundamental level in FSC or in the metric 2. So all we did today is that we tried to give that concept that you already had a mathematical model. Okay, so you basically uh, wrote whatever you already understand in the form of equation, and that makes sense because we know that the magnetic field was being generated due to the first coil, and we know that this field was linking with the second coil, so we integrated it according to the surface area of the second coil. And then we talked about that if we want to calculate the total magnetic flux linkage between these two coils, then we'll have to take into account all the number of turns that are present in the second coil. So we took into account all the number of turns that were present in the second coil, and we multiplied that with the flux that was passing through a single turn. And once we multiplied that, we had the value of magnetic flux linkage, and after that we had to divide that magnetic flux linkage with the amount of current that was producing the magnetic flux in the first place. We divided that, and as a result we have derived an expression for mutual inductance. So this is it for today. In the next lecture, we're going to talk about magnetic energy, and that is going to be our last topic for this course. If you have any confusions, you feel free to ask them in the interactive session. Thank you so much.